Okay, great. So thank you everyone for joining this session. Thank you again for your time. And in this session, we are in module 3 and the second session of module 3. So in module 3, we're talking about the wireless LAN MAC layer or the medium access control layer. And in this session, we are going to specifically talk about MAC layer headers and frame formats and different types of frames that you would see in the MAC layer, and the various headers and the fields within the headers and the key functions of these fields within the different types of MAC frames that we have. Before we jump into this session, let us quickly recap what we talked about in the last session. So last session, we introduced this concept of a wireless LAN basic service set. We said that normally in a wireless LAN, if there is only one transmitter and one receiver, then the problem is very simple. There's only one transmitter and one receiver, and then we're only thinking about the physical layer. But that's not how a normal wireless LAN cell works. In a wireless LAN cell, there is an access point and there are multiple devices, which means multiple devices have to figure out a way to access the medium successfully without interfering with each other, right? And then there is also we talked about multiple clients talking to the access point, and then there are multiple cells or multiple access points in the wireless LAN network. And how do all these interoperate and how do they successfully coexist is something that we discussed, right? And we also explained this, use this analogy of how things work in a college or in a school, where the main goal is for the teacher to teach the student, but then there are many students, there are many teachers, there are many classrooms, and there are many sessions that need to be organized and rules and regulations that need to be followed in the school. So there is management overhead, there is control overhead. The management will actually set up various policies and rules within the organization. They'll schedule the sessions, they schedule the classes, classrooms, and so on. And then there are various types of controls that are there that need to be put in the college for it to operate in a nice way. So similarly, in a wireless LAN network, we said that there is a lot of management and control functions that are overhead, that are on top of the data communication. So data communication is basically where the transmitter is sending information to the receiver, but then around that, to make that successfully happen, there's a lot of overhead in the form of management and control. So we talked about that. We introduced the concept of a basic service set and an extended service set. We also explained the terms SSID, which is the name of the network. We talked about BSSID, which is the unique MAC address of a physical access point. We explained the concept of SSID, which is a logical name for the network, and that same network can exist on one or more physical access points. We talked about the concept of beaconing, which is basically the menu of the access point. So an access point constantly sends out these beacon frames or messages once every 100 milliseconds, and they advertise the capabilities of the access point. And then that is what the station will use to figure out what access points are available to connect to. And the beacon frame contains a whole bunch of details about that particular access points. We talked about how beaconing works. We talked about how scanning works. We talked about the concept of active scanning and passive scanning, and how the device populates its network list by doing various methods of scanning. And then we talked about basic client connectivity, how a client successfully connects with an access point using various methods, using open authentication. We talked about how you can connect using basic security, like a pre-shared key method. We talked about how to connect using a browser-based authentication or captive portal. We discussed those, and then we also touched upon various management and control functions of an access point, such as load balancing, band steering, power save. Talked about how DFS works, and a number of other basic management and control functions. We talked about how virtual carrier sensing works, RTS, CTS frames, what do they do on the network. We discussed all those things, mostly concepts of the MAC layer. And the basic idea was, what are the various management and control functions that make medium access or multiple access work in a wireless LAN network? And how do you make sure that all these devices, all these access points, all these clients they all can exist in the network without any problems, right? And that is mainly what we were discussing about management and control functions. So if anyone missed the previous session, the recording is on the website. You can actually go and watch the recording, and the slides are also uploaded, so you can certainly go take a look. So today we are going to talk about the actual frames and the frame formats from all these various concepts that we talked about, right? So what is a beacon frame? What is a probe request frame, probe response frame? What are its contents? What are its header elements? We're going to talk about all those things in this session. So if you look at our OSI model again, on the top left-hand side, we said that wireless LANs operate primarily in the physical layer and the data link layer. So we talked about the physical layer in the last module. We said that physical layer has two sublayers, the PLCP layer and the PMD sublayer. Now we are into the data link layer, and the data link layer also has two sublayers, the logical link control and the medium access control, or the MAC. Basically. So if you look at how the frame formats worked in our in module 2, we explained how the physical layer headers work. We have the PLCP frames and we have the PLCP header. The PLCP header has the preamble and also some other information about the frame itself, right? Normally, you can think of a header as if you want to read a book, let's say. The book has all these chapters and all the content, and you can consider that as the body of the book. And then you have the table of contents, which is in the very beginning of the book, in the first page, right? And the table of contents tells you about what to expect within the book. So the header is somewhat like the table of contents. It contains information about what's inside the book and what to expect. And that is what really the header is. So at each layer in the OSI model, there are headers. So the physical layer, there are physical layer headers, and the MAC layer, there are MAC layer headers. At the IP layer, there are IP layer headers. We talked about that in one of the previous sessions, where we gave this example of how you have a ball of chocolate and how it's wrapped in many layers, and each layer has various functions. Similarly, if you look at in this particular section, this is a physical layer frame, and the body of that frame is called as the PSDU, or the PLCP service data unit, or PSDU. This is nothing but your MAC frame, or the MAC layer frame, including the MAC layer header. So inside the PSDU, you have the entire MAC frame, including the MAC header and the MAC payload, right? So what is the MAC payload? Again, it is the IP packet, including the IP header and so on, right? So that's how the layering actually works. So now if you look at the MAC frame, so this is basically a quick overview of what is the MAC frame. MAC frame meaning the 802.11 frame. And this is how the frame actually looks. At the highest level, there are three parts of this particular MAC frame. The first one is the header. The header will give you more information about the entire frame. And the header is one of the most important parts. And one of the things to remember is the header is normally transmitted first. So for example, if this particular frame is being sent from the transmitter to the receiver, then the header is going to be transmitted first. So when the receiver receives that is the first information it receives. And when it looks at the header, it can look at the details in the header and decide what to do with the next part of the frame, right? Which is why the header information is normally transmitted at the very beginning, right? And that's why it's called the header, because it's the beginning part of the frame. The tail end of the frame has what we call as the FCS, or FCS is nothing but an error checking mechanism to make sure that this particular transmission doesn't have any errors. So normally FCS is calculated on the entire frame using some calculations, and then when the receiver receives that particular frame, it will recalculate the checksum or the FCS based on the calculation algorithm. And if the calculated FCS doesn't match the transmitted FCS, then it knows that there is some errors in the frame body, right? There are the packet errors. So FCS is a mechanism to basically detect errors on the link. And then in the middle, you have the frame body. So in this side, you have the frame header at the beginning. On the back, you have the protection mechanism for the frame. And within that, you have the payload, which is the frame body. So that is basically what a MAC frame is. Now, let us see what is this header. The header contains a lot of information, right? So if you expand on the MAC header, then it contains all these fields. So there is the frame control field, there is the duration field, there are the address field, sequence control, and so on. So the address fields are nothing but, remember that this is a layer 2 frame or a MAC level frame. So the address fields are nothing but MAC addresses, right? And they are 6 octets or 48 bits basically long. And each one of them is a specific MAC address, right? And what those addresses are, and we'll talk about that in the next few slides. Now, the most important part of this MAC header is one of the most important parts is the first part, which is the frame control field. The frame control field is 2 octets or 2 bytes, right? And this one has, if you break it down into and look into the details, these are all the subfields within the frame control, right? So frame control is 2 octets, and then these are all the subfields within the frame control. So what does the frame control have, and which is basically the very first part of the frame, right? So what does it have? It has the protocol version, which tells you what version of the .11 protocol are we using, and then it has the very important type and subtype fields. So type and subtype represent basically the type of frame. In the previous session, we talked about the management frames. So we said that the access point has 3 main functions or planes. There is a management plane, there is a control plane, and there is the data plane. So the data plane, of course, is used to carry data, but then the management plane is used to manage the wireless network, and the control plane is used to set certain controls on the wireless network. So there are really 3 types of frames. So management, control, and data. So that is what this field subfield represents. So it's 2 bits. So there are 4 combinations: 00, 01, 10, and 11. So if this type is 00, that means it's a management frame. If the type is 01, it means it's a control frame. If it is 10, then it means it's a data frame. So that is how the type field works. There are only 4 possible combinations, and there are three types of frames. And then you have the subtype, which is 4 bits, and so it gives you 16 combinations. Under each type, there are several subtypes of frames. So for example, under management, there could be beacons, probe requests, probe responses, authentications, de-authentications. There are many different types of subtypes of the management frames, and they all have one ID, right? Each one of them gets one combination of these 4 bits. And so the receiver, when it receives this frame, if the type field is set to 0, 0, and the subtype field is set to, let's say, 1000, then it knows that this is a type management and subtype is beacon frame. So now when the transmitter is sending a frame with the type set to management and subtype set to beacon, when the receiver receives and processes those bits, it knows that it is now receiving a beacon. And now it is going to look at the rest of the bits and bytes in the frame, assuming that it is a beacon, and it's going to decode the rest of the information like it would decode a beacon frame. Now, if the type is set to data and subtype is set to a certain type of data frame, then it will assume it's a data frame and it will process like it's a data frame. So that is the reason why the type and subtype is very important, because based on that, the receiver processes all the remaining frame based on what it is what the type and subtype are. And then there is something called as 2DS and from DS bits. These are also very important bits that I'll talk about in the coming slides. And then there is a duration field. The duration field will basically tell you how long this packet or this frame will need to be transmitted on the air. So it basically is the duration of the particular frame. And then we have the address fields. There are 4 address fields. Not all of them are used in every frame. So you can see that if you look at the color notation, everything that is in green is a mandatory field that has to exist in every .11 frame, right? The one in the more of the orange color are basically also mandatory. They exist in all the frames, but their length can vary based on the type and subtype, and some of them the fields can vary a little bit, and the contents of the field can also vary a little bit based on the type and subtype, right? And the ones in yellow are optional, so they are not present in every type of frame. They're only present in some types of frames. That's the notation that this particular diagram has. So now coming back to the address fields, there are 4 address fields. The first 3 are mandatory. That means they are in pretty much most of the most of the .11 frames. And then the address field is 4th field is optional, right? So what are the contents of address 1, 2, and 3? We'll discuss that in the coming slides. So now looking at this in a little bit more detail, if you look at the frame format, this slide will give you the definitions of each and every subfield and subfield. Under the frame control, you have the protocol version, which is 2 bits long. It tells you the protocol. We talked about the type. There are 3 types: management, control, and data. We talked about the subtype, and then we have the 2DS and from DS fields. We talked about those things, and we'll talk about that in the next slide in more detail. And the more fragment field, it represents if there are more fragments. So .11 supports this concept of fragmentation, where you can take a larger payload and break it down into smaller chunks and send them in different frames. So then you have this concept of fragmentation. So if you're sending multiple fragments, then this field will tell you there are still more fragments to be received. So then the receiver knows, okay, I am only receiving fragment number 2. There are more fragments to be received. So then it can actually wait for all the fragments to come before it reassembles all the fragments and sends them to the upper layer. So that's where the fragment bit is used. And then there is a retry bit, which is a very important bit. Yes, in the last session, we talked about the concept of retries or retransmissions. So when a data frame is sent from the transmitter to the receiver, if the receiver doesn't get the data frame, the transmitter has to retry it. And so when it retries the frame, it can set the retry bit in the header. And when the receiver sees the frame with the retry bit set, then it understands that this is a retransmission, right? Similarly, there are power management bits, more data bits that are used for various functions. The power management bit, when it's set to 1, then the transmitter is telling the receiver that it's actually about to go to sleep. It wants to go to sleep and get into a power save mode. So these bits are used for various management functions in these frames. Similarly, I mentioned there is the duration field. There is something called as a sequence control field, which will tell you the sequence number of the frame. And sequence numbers are normally used at the receiver to make sure that the frames are received in the right order. So if the frames are received out of order, then basically the receiver can look at the sequence control field and reorder the frames. And then of course we have the data part of the frame, which is the payload. And you can see that even though in this picture it shows to be a very small section, this could be the longest section of the data frame. It could be all the way from 0 to 2300 plus bytes of information. So that's the payload. And this is all the header information. This is the payload. And then at the end, as we mentioned before, there is the CRC or the FCS for error checking. Okay, so we said we were going to talk about this 2DS and from DS fields. This is basically an interesting idea, because if you look at for those of you who might have followed the wireless LAN topologies class, we talk about the different types of topologies and how Wi-Fi is deployed in various topologies. There are many ways in which Wi-Fi is deployed in various types of topologies, and the 2DS and from DS bits are really useful for that. So the first option is, what does DS actually stand for? DS is the distribution system, or it also refers to the network that is behind the access point. So anything that is behind the access point, which means that, remember in last class we talked about a wireless LAN cell, and you have an access point and you have the devices in the cell. Anything outside that is the distribution system, outside that wireless LAN cell. So going to the wired network is the distribution system. So now if your 2DS bit is set, that means that you are sending information from inside the wireless LAN cell to the distribution system, to somewhere outside. So from inside to outside. So which means you are saying 2DS. If you say from DS, that bit is set. So that means that that information or that frame is coming from outside to inside the wireless LAN cell. So it's coming from the wired network or from the internet inside the wireless LAN cell. If you do not set the 2DS and the from DS bits, if both of them are set to 0, that means that the transmitter and the receiver, the source and the destination, are within the wireless LAN cell. They are not going outside, right? So for example, if there is if my phone is talking to this access point and it is sending a packet. So for example, this access point is sending a beacon and my phone is receiving the beacon. That beacon is not intended to go to the wired network. It is not going to the internet, right? It is only staying within the wireless LAN cell. Let's say this guy sends a probe request to the access point. The access point receives the probe request and he sends a probe response. Those frames are only between this client and this access point. They are not going outside this wireless LAN cell. They are not going to the internet. They are not going to the wired network. So those frames that have to stay within the wireless LAN cell, typically all your management and control frames normally have those 2DS and FromDS bits set to 0. So when the receiver is receiving something and it is seeing the 2DS and FromDS bits are set to 0, that means it knows that that packet or that frame terminates there. It doesn't go further. It basically stops there, right? On the other hand, if you want to send a data frame from the device to the network, to the internet through this access point, so the phone, the client, is sending a frame to the access point, which is intended to go to some destination address on the internet. In that case, when the phone sends a packet, it will send the 2DS bit to 1, which means that it is indicating that the frame is going to the network, and it will set the FromDS bit to 0. So if it is going to the infrastructure, the 2DS bit is set to 1, the FromDS bit is set to 0. If it is coming from the infrastructure, from the network side, then it is from the AP, then you set the 2DS bit to 0 and the FromDS bit to 1. And the last combination is normally what we refer to as a bridge mode. This is where we're bridging two Wi-Fi networks. In this picture at the bottom, you see that there is one wireless network that is connected to the access point. So when we talked about wireless LAN bridging, we talked about two networks, possibly wired networks, that could be bridged using wireless access points. So here you have one wireless network that has an access point, and then you have another network that has another access point, and these two are connected using Wi-Fi, right? So this is normally referred to as a bridge mode. In this mode, what we are doing here is we are setting both the 2DS and the FromDS bit set, because it is coming from the DS to the AP, and then from here it is going to the DS again, to the other side of the distribution system, right? So you have both the 2DS and FromDS bit set in this particular case. So the three models are 2DS when the client is sending to the AP to the network, FromDS when the network is sending the packet of through the AP to the client, and then you have both the bridge mode, right? These are the three options. Now, if you look at the address fields, the 4 address fields we talked about, if you go back to the previous slide, there are 4 address fields: address 1, address 2, address 3, and address 4. These address fields have different addresses based on these bits. So for example, if both the 2DS and FromDS bits are set to 0, that means the frame is staying within the wireless LAN cell. Then address 1 is the destination address, the address 2 is the source address, and address 3 is the BSSID, right? So and depending upon who is sending it. So for example, if the client is sending a probe request to an access point, then the source address is the client's address, the destination address is the access point's address, which is also the same as the BSSID. So the DA will also be the BSSID, and then the address field is the BSSID, right? So if the AP is sending to the station a management frame, then the source address is the BSSID, the destination address is the address of this phone, and then the BSSID is again the same, the BSSID of the access point. So if you are set in this mode, in IBSS mode, when you have 2DS and FromDS bits set to 0, address 1 is the destination address, address 2 is the source address, address 3 is the BSSID, and address 4 is not needed, not used. If the packets or the frames are going to the infrastructure, then the first address field represents the BSSID, the second address field represents the source address, which is the station's address here, and then the third address field represents the destination address, which is the network destination address here. If the frame is coming from the network, then you have the FromDS bit set. In that case, the first address field is the destination address, the second address field is the BSSID, and the third address field is the source address. And if you are in the bridge mode, then you need all 4 address fields: the source address, the transmitter address, which is the AP, the receiver address, which is the other AP, and the destination address, which is the final destination. I know this is a little bit confusing. It's a little bit hard to explain in just a few minutes without confusing you. I'm probably confusing a lot of you now, but if you spend a little bit more time and go through this in more detail in your free time, I'm sure you can understand this better, right? It's really hard to explain this in a nice way within 2 to 3 minutes. But that is the idea. The address fields, there are 4 fields, but the contents of the fields will change based on from where to where the data is the information is being sent. Okay, so if you look at to summarize again, frame types and subtypes, there are 3 frame types. That is the management frames, control frames, and then there is the data frames, right? The management frames have all these subtypes like beacons, probe requests, responses, authentication, association, de-association, and so on, disassociation, and all of that. And then what happened is, so a lot of what you're seeing here is from the base standard, from the base .11 standard, ABG, Wi-Fi 1, Wi-Fi 2 days. But as we went into Wi-Fi 3, 4, 5, 6, and 7, with every new standard, there is new technology or new features being added, right? When we came to 11N, we had aggregation, right? So when we had aggregation, that means that the transmitter can send lots of frames at the same time without waiting for an acknowledgement. In previous session, we said that Wi-Fi uses the stop and wait protocol, where it sends a data frame, waits for the acknowledgement, and then sends the next data frame. Now, if you have aggregation enabled, you can send so many data frames one after the other without waiting for an acknowledgement, and then you get something called as a block acknowledgement back. Now, we'll cover this in more detail in the coming sessions. So we need new action frames or new management frames to actually manage these features. So just like, let's say someone introduces a new course in your college. We want to add this Wi-Fi course in your college. Okay, then we need to find a teacher for that, and we need to find students, but we need some overhead to manage that class. So we need to create the course curriculum, we need to create the labs and the exercises and exams and the schedule and the course sheet and all of those things, right? So that's all the overhead. Anytime you have a new feature, you need some overhead around it. Similarly, as the new protocols start getting added, like aggregation got added, so there are new management frames that can actually manage the aggregation function, right? So when better transmit power controls, radio resource management features got added, then there is transmit power control frames that got added. When we added beamforming or multi-user MIMO, then we have the sounding frames that is not listed in this slide, but there are new management frames and action and control frames that have been added to actually make sure that that feature works properly, like multi-user MIMO. When we added OFDMA, then we have this concept of trigger frames that are again new frame formats that are there to make sure that feature works well. Similarly, in Wi-Fi 7, when you have a feature like MLO, there are new frames that will actually make sure that that particular feature works well. So every time there are new features in the standards, there are new management frames that are added. Now, since we don't have a fourth subtype that is being used, there is this new category called action frames that is created, that is also under the management section, right? Management frame section. And under that, you have all these new frames that are available, right? So broadly classifying, you have management, control, and data frames. Now, in the data frames, we see all these different types like QoS data and all that. Most of it you can ignore. The main really things you want to remember are the QoS data and the null data frame. All these others are mostly not used, and they were actually created when in Wi-Fi, in the early standards, Wi-Fi standards, there used to be this PCF technology, or what we also refer to as contention-free mode, where the AP can take over the medium access and say, I am going to now take over the medium completely, and I am going to schedule transmissions. So the AP can say, okay, I have 10 clients connected to me. I am going to give each client a time slot to transmit, and I am going to manage the medium access, right? And that is called as a contention-free portion of the protocols, and that's where the CF came from. And there were a number of frame formats for the contention-free protocol that were used. But for some reason or the other, the contention-free mechanism never really took off. The PCF or point coordination function, as it was called, never really got implemented by most AP vendors. And so those features are really not used. So in the data frames, really you're only looking at QoS and which QoS data frame, which has the data frame with the QoS header and also the payload, IP payload. And then there is a null data frame, which is used for certain use cases, which I'll talk about later, without any frame body. There is no frame body. It is just a null frame that is being sent. Under the control frames, we talked about CTS, RTS, acknowledgements, and so on. Those are the main ones. We also have PS poll, which is used for power save, which we'll talk about later. And then we also have other frames like block ACK request and block ACK response that is used for the aggregation feature. Right? Okay, so now if I move on further and if I look at things like the summarizing again in a different format, now we have this frame type and subtype fields. This is a little bit more detailed. So you can see all the frame types like type 0, which is all the management frames. Under that management frames, you have all these subtypes with all these individual codes. And then control is 0, 1, and you see all the control frames, different types of control frames. And then you have the data, and then these are the subtypes for all the data. And there is some extension. One would be used for extension. And then there are reserved for certain new types of frame formats, management and control frames that will be used for future protocols. Basically, this is just a table that shows all the data. And this this slide also shows how the management and control frames actually work. So as we talked about in the header, this is a classic Wi-Fi frame, which has again the frame control, duration field, and the address fields. This is common. The header is common for every type of .11 frame, but the frame body will change. For example, if it is a management frame, the frame body will have information about that particular management frame, but the headers will remain the same. So as you can see in this example, the headers showing the first address field as a destination address, the second address field as a source address, and the third address field as the BSS ID. Why is it doing that? Because it is from DS and 2DS are set to 0. If you go back to this slide, so from DS and 2DS bits are set to 0, which means the first address field is the destination address, the second address field is the source address, and the third address field is the BSS ID. Right. So if you go back to the current slide again, the first address is the destination address, second one is the source, and third one is the BSS ID. So this is the header of the management frame, right? And then what is inside the body will vary for each management frame. So for if it is a beacon, you will see these fields inside the body, right? If it is an association request, you will see these fields. If it's a reassociation request, you'll see these fields. All of this will change based on the type of management frame. We'll talk about that in this in more detail in the coming slides. So when we come back to the connection state machine of a client with an access point, these are the various states in which the client can be with respect to the access point. So the client could be in state 1, which is it knows that the access point exists, but it is not authenticated and not associated with it, right? And that's state 1. Now, if it finished the authentication process, then it has successfully authenticated. So then now it's in state 2, which is authenticated but not associated. So once it finished the authentication process, then if it does an association process, either association or reassociation, now it is fully authenticated and also associated, which is state 3. And then after that, if it does all the security handshakes, now it's authenticated, associated, and also ready to send data. So these are generally the 4 states in which the client can be with respect to the access point. Now, of course, the client can transition between these states continuously. For example, if it's an authenticated state, it can send a de-auth to the API, and then now it pushes that back into unauthenticated and unassociated state, right? If it sends a disassociation from here, then it can be in an authenticated but not associated state. So these are the various states in the state machine of a particular client, and all these frames that we're talking about can actually put the client in various states. Why is this important? We'll talk about that in the next few slides. So let's now come back to one of the main management frames that we are all talking about, which is the beacon frame. Right? This is one of the most important frames. As I was saying before, the beacon frame is nothing but the menu of the access point. It contains all the details about the access points, and it is advertised and transmitted in a broadcasted once every 100 milliseconds in general speaking. So this is the beacon frame format. Again, as I said before, the header is the same. The header will have frame control, duration, address fields, and so on. The body itself will change. And if you look at the body of the beacon frame, then it will have all this information inside the body, right? And there are 2 types of parameters inside a beacon frame. One is what we refer to as a fixed parameter, and that fixed parameter is always fixed in all the beacon frames. Every beacon frame has the fixed parameters, right? And then there are the tagged parameters. Tagged parameters are optional or variable parameters, so they can change based on the different types of beacons, right? So some APs might have only 3 tagged parameters, some might have 5, some might have 10, based on its capabilities. Just like a restaurant's menu, it could be a simple restaurant and it could have only 4 items on the menu, or it could be a very fancy high-end restaurant with which is a multi-cuisine restaurant. It could have a 10-page menu with like 200 items on it, right? And that could vary based on the capabilities of the access point. And those parameters are called the tagged parameters. The fixed parameters are the most important ones that are mandatory, that are required for every beacon frame. The tagged parameters can vary based on the what the capabilities are for the access point. So what do we have in the fixed parameters? The first one information that we have in the fixed parameter is what we refer to as the timestamp. And timestamp is a very important parameter for the beacon frame. So what is this timestamp and why do we need it, right? The timestamp is nothing but the access point's clock information, right? And every station that is connecting to the access point need to synchronize with the access point's clock for various reasons. So just to take a very simple example, let's say you walk into a classroom and the teacher is about to start the class, and there is a clock on the wall and that says 4 p.m. right now, right? And that's the clock on the wall, and that is the clock that the teacher is going to follow for the rest of the class. So if the teacher is going to give a pop quiz at 4:15, then it is going to look at the clock which is in the classroom, and when that clock hits 4:15, then the teacher is going to give out a pop quiz. Now let's say I am entering as a student into the classroom and my watch is like 5 minutes faster than the clock on the wall. So when it says 4:15, my watch says 4:20, right? Now that's not going to work out. I cannot tell the teacher that I'm following my watch and so I'll miss the pop quiz. I cannot say that, right? Because the teacher is expecting me to follow the clock in the classroom so that it can listen to the right information at the right time based on the clock that's in the classroom. So which means that every student that's entering the classroom needs to synchronize their time with the time on the wall in the classroom. Similarly, every station that is coming into the basic service set that is connecting to an access point need to synchronize with the clock of the access point so that it can receive some information, some time sensitive information from that access point. So what is the time sensitive information? There are many different types of things. There are when the client goes to sleep, when to wake up to receive information. There are many things like that are time sensitive information. And so without being properly synchronized with the AP's clock, you will not be able to receive that information. So that the timestamp is critical, and it is broadcasted once every 100 milliseconds, right? Similarly, we have the beacon interval in the fixed parameters. The beacon interval will tell you the interval at which we are seeing the beacon. So normally it's set to approximately 100 milliseconds. So which means that every 100 milliseconds, the AP will send a beacon frame. So sometimes the AP can say, I don't want to send beacons every 100 milliseconds. It's taking too much overhead. So maybe I'll send a beacon once every 200 milliseconds, and it can change the beacon interval. Normally, none of the APs do that, right? And then there are a number of tagged parameters that contain various fields like the SSID, the supported rates, and so on. So let me quickly show you a beacon frame in a wireshark capture. So if you look at this wireshark capture, for those of you who have not seen wireshark capture before, remember wireshark is this magical tool that can basically see what we cannot see with our eyes. It can see packets in the air, and it will basically capture all the packets through the radio interface, and then it will decode the bits and bytes, and it will represent those frames in the form of text. So that's in front of us, we can see the beacon frame right now. And if you look at the details of the beacon frame, which is on the right hand side, you can see the beacon header. Again, this header is the same for all types of frames. So in the header, you will see the type and subtype. So it says type is management, which is 00. The 2 bits, remember there are 2 bits allocated for the type. So it's set to 00, and then the subtype to 1000, which represents a beacon frame. So type and subtype are here. All these other flags we talked about in the frame control, the more fragments, the retry flag, the power management flag, the order flag, and all these other things are all inside here. And then you can also see the from DS and to DS bits that we talked about. They are also in this flag section, or also referred to as the frame control section. So you can see here, since it's a management frame, the to DS and from DS bits are set to 0, which means that this particular frame is only going to be within this wireless LAN cell, between the access point and the devices. So the flags are already there, right? It's all you can see all of them. And then there is a duration field, and then we have the address fields. There are 4 address fields that are provided here. So in this particular case, since it's a beacon frame, the source address will be the address of the access point that is sending out the beacons, the MAC address of the access point, and the BSS ID will also be the same, because the BSS ID is the same as the MAC address. So you'll see the BSS ID is also the same. So this is the header of the beacon, right? And then you also have the FCS, which is a trailer, and then you also have the fragment number and sequence number. All these are part of the frame header. If you go back and look at the frame header that we talked about initially, they're all there. The frame control, duration, address field, sequence control, and then under the frame control we have type, subtype, more fragments, retry bit, power management. You can see all of those things here inside the header of the beacon frame, right? Now we come to the body. The body is the different section. So now we are done with the header. We look at the body. So under the body, we said that there are 2 types of parameters: fixed parameters and tagged parameters. So this is what I was showing in this slide here. If you look at the beacon frame, so we said that there are 2 types of parameters: fixed parameters and tagged parameters. So now going back to the wireshark capture, so we have the fixed parameters and the tagged parameters. Under the fixed parameters, you have the timestamp. As I mentioned, that is the timestamp for the time of the clock information about the access point. We have the beacon intervals, which is approximately 100 milliseconds, and then we have the capabilities, which will tell you a little bit about the access point. Not too much, some information, little bit of information you get, right? Like if it's using short preamble or long preamble, and a few other information like that are relevant to that particular access point. You can find that. Is it an access point? What mode is the device operating in? Is it operating in an access point mode, or a bridge mode, or a station mode? All those details are there in the capabilities. Now you go to the variable parameters, the tag parameters. You see there are a whole bunch of tag parameters. So every tag parameter represents something in the menu, right? So the first and the most important tag parameter is the SSID, or the service set identifier, or the network name. So if you look at every tag parameter will have 3 components in it. One is the tag number, the number of the tag length, how long is the tag, and then the tag data, which is in this case it's the SSID. So now this is saying that this SSID is open Wi-Fi _ 5 gigahertz. So this is the SSID, the information that my phone is reading when it's reading the beacon. When it sees the beacon, the phone, my client will actually look for the tag parameter and say, okay, I find this SSID called open Wi-Fi. I'm going to read that information and I'm going to display that in the list of my wireless networks, right? So that is where this particular information element is used for. There are a number of other information elements like supported rates. So this is going to list all the rates that this access point supports, all its capabilities. So for example, this access point is able to support 6 Mbps, 9 Mbps, 12 Mbps, 18 Mbps. So for those who attended the class on modulation and coding schemes, all of these correspond to different modulation and coding rates, right? These data rates, right? And all these data rates are supported by this particular access point. And some of them are what we refer to as a basic rate. So if you see a B next to a data rate, that means it's a basic rate. So basic rate means that any device that is connecting to this access point that is sending out this beacon in this wireless LAN cell has to support those rates. If it doesn't support, if let's say this device tries to connect to this access point and it doesn't support 24 Mbps data rate, then this access point will not allow this client to connect, because 24 Mbps is advertised as a basic rate. That means this client should be able to support at least 24 Mbps data rate to be able to connect to this access point. Why? Because the most common frames like management frames, beacons, control frames, and things like that can be sent at any of these basic rates. And the understanding is that the most common frames in the wireless LAN cell should be sent at a basic rate where everyone in the wireless LAN cell should be able to understand. So which means that if you're not able to understand the basic rate, then you should not be in that wireless LAN cell. You should be outside the cell. You should be connecting to some other access point. So what this means is, while there are optional rates, there are certain rates that are mandatory rates that every device in the wireless LAN cell should work in, and those are the basic rates, and that's what this device is advertising. So for example, when my phone tries to associate with this access point, it sees this list and it says, oh, okay, I can support all these rates, but I don't think 24 Mbps is a basic rate for me, so there is no way I can connect with this access point, and it will not try to connect to that access point. So that's where this information is used. We also have channel information, and we also have lots of other information element, country code information. In the interest of time, I'm not going to go all of that, but this will tell you like what country code or what country this particular access point is operating in, and each country has a certain set of rules for transmit power. So for example, this access point is operating in the country code CA, which stands for Canada, and then for Canada, these are the rules. When you're operating in these channels, you should be able to send maximum transmit power of these values, right? So it tells you that information. You also have lots of other things like the QBSS load element, which tells you how much medium utilization is on this access point, how much channel utilization it has. When the client sees that QBSS load element, it can say, oh, this access point already has like 70–80% medium utilization. That means it's already busy. So maybe I don't want to connect to it, right? So it tells you how busy this access point is. That information is there. There are lots of other tags that represent security. Now, if this access point supports Wi-Fi 5 technology, then or Wi-Fi 4 11N, then it can support these HT information elements, which are high throughput information elements. If it supports Wi-Fi 5, then that is very high throughput. Then you have Wi-Fi VHT information elements. If it supports Wi-Fi 6, then it has HE information elements. HE stands for high efficiency Wi-Fi. So now this access point can do Wi-Fi 4, Wi-Fi 5, Wi-Fi 6, because it has all the Wi-Fi 4 information elements, Wi-Fi 5 information elements, and Wi-Fi 6 information elements. Plus, it can do the legacy also. And that's what this access point is telling from this particular beacon. And there are a number of other information elements. In the interest of time, I'm not going to go through all of them, but it gives you the full list of things about the AP. Now you know that just by listening to the beacon, you can find out so much information about any given access point, and the device can track all the information, and it can create the list of wireless networks. So now going back to our beacon frame here. So that's what the beacon frame has. Now there are a number of other frames, we have this concept of probe request and probe response frames and so on. Again, this is part of the association. In the last session, we talked about active scanning and passive scanning. So the probe request and response frames are a part of the connection process. Again, if you see a probe request frame, all the MAC header is the same. MAC address is the same as all frames: frame control, duration, address fields, and so on. But the payload, meaning the frame body, will change, right? And then even the probe response, the frame body will change. If you look at the probe response, it will have information about the probe request will have information about the station connecting to the access point, and the probe response will have information about the access point responding back to the station. So those frames are there, right? If you look at the authentication frame, again, the MAC address is the same. The body will change. And in authentication, you have certain fields, like you have the authentication algorithm number that represents the type of authentication we're using. So normally we have this open system authentication and shared key authentication. So if you're using open system authentication, then your algorithm number is set to 0. And if you're using shared key authentication, then your algorithm number is set to 1. And then you also have the transaction sequence number. So if you're sending an authentication request, that is sequence number 1. If you're sending an authentication response, then that is sequence number 2. So that's what these fields represent. And then there is the status code inside the frame body. The status code will tell you if the authentication was successful or it failed, right? So those are some of the information in the authentication frames. Again, authentication is a basic authentication process. This was part of the base .11 standard, and they implement this very simple authentication process, which can be either open system based, or it could be based on what we call as a shared key authentication, where there is a basic encryption. where you send a challenge text from the client to the AP, and the AP encrypts that using a password, and then the client decrypts that, and then from that they basically say, okay, you have the right password, now we can talk to each other. It's a very rudimentary kind of security mechanism which can be easily cracked, right? But those are the authentication methods that were available in the base standard. Very quickly people realized that those methods are really not going to be practical, because they can be easily cracked, and they are very insecure. And so later we came up with so many different security protocols, the .1x authentication, a number of other security protocols, which we'll talk in the next module. Next module is all about security. But the base standard authentication is very simple. Either it's open, where you can openly connect to the network, or you can have a simple password and you can exchange some information. And that is what the authentication frame does. So once you're authenticated at the .11 level, now you have something called as the association. So now you're associating with the access point. Now we mentioned this last time. So the process is very straightforward. The client will send an association request, and it will again tell about its capabilities. And the AP will look at the association request and say, okay, I can admit this client, and I have the bandwidth to serve this client, and this client is compatible with me, which means that, let's say if AP, remember the AP is saying 24 Mbps is a basic rate. If the client also advertises 24 Mbps as a basic rate, then it is compatible with the access point, right? Just as an example. So it will check for compatibility. The access point will check for compatibility and also check for available bandwidth. And if it is able to admit the client, then the AP will send an association response. And in the association response, there will be this status code which shows successful, and there's also this association ID, right, which is basically the identifier for the association, a number for the client. So these are the fields inside the frame body, basically the status code and the association ID. These are the main fields in the association frames. Similarly, there is this concept of reassociation, where if you are associated with the particular access point and you lost association and you want to reassociate, you can use this concept of reassociation frames. And then the reassociation can happen with the same AP, or it can happen with the new AP. And how it works with the new AP and all that, we'll explain in more advanced features like roaming protocols and things like that. We'll explain that at that point. But there is something called as a reassociation frame, where you don't have to go through, if the client is already in an authenticated state but not associated, it doesn't have to go through the whole process of probing authentication again. It can just send a reassociation request and connect to the access point. And that's where the reassociation frames are used. Similarly, you have de-authentication frames, where you want to disconnect from a Wi-Fi network. So when you want to disconnect from an access point, then you can basically send a de-authentication frame. The client can send a de-authentication frame. This is again a management frame. And then inside that, you can have a reason code. You can give a reason why you're disconnecting. And then the reason codes have various meanings, right? These are some of the reason codes that the station can provide to the access point. The access point can also send a de-authentication to the station, and that basically is forcing the client to disconnect from the network. The client can send a de-authentication to the AP when it's leaving the network. The access point can send the de-auth to the client when it wants to kick the client out of the network, right? So this can go in both directions, right? And that is the de-authentication frame. Similarly, there are these RTS CTS frames, which we touched upon it last time. So RTS CTS, what it does is it really tries to solve what we call as a hidden node problem, right? So what that means is, let's say you have a Wi-Fi access point here. This is basically in the middle here, an access point. And then you have one station here and another station at that corner. Now, both stations want to send information. So this station here and this station here wants to send information. They can both hear the access point, but they cannot hear each other. So this client is too far away from this client. They cannot hear each other. So then if they're both transmitting at the same time, there will be a collision. So this is called as a hidden node problem. So to avoid the hidden node problem, what the station 1 can send an RTS, or a request to send frame, which the AP will receive. And in the RTS, there will be a duration field. You can see that there is a duration field here. And in the RTS, the station is saying, I want the medium for this amount of time, for this duration. And then the AP will look at that and say, okay, fine, I can give you that amount of duration, and let me send a clear to send, or a CTS frame, clear to send. And it's a broadcast frame, and it will send a clear to send frame and in that frame it will tell you how much duration or how much airtime it is giving to the station. Now when that frame is sent out, the other client which can hear the AP will now see the CTS frame and say, okay, there is a clear to send frame, which means the AP is about to communicate with some other station, so I need to back off. I need to get away from that. I'm not supposed to access the channel for whatever is the duration in the CTS. So that is basically how you avoid hidden node problem, and it's also called what we refer to as virtual carrier sensing. Here you're not doing physically, you're not doing carrier sensing, but virtually you're doing carrier sensing by using these frames called CTS and RTS. Now, in the interest of time, I'm not going to go into all the details, but there's a lot of information available online, and we can also provide more details in the notes. And after all these frames, all the control frames, management frames, all these override frames, finally we come to the data frame, which is really the payload. That is the only thing that's really useful at the end of the day, because that is what's carrying the information that you care about, right? But everything else is extra overhead, and without the overhead, you cannot successfully send and receive data frames. So then the data frame is also very similar. It has all the same header information, but then it has the frame body, which is nothing but the IP payload, and that IP payload could be thousands of bytes, right? And based on the size of the frame itself, right? And that is the data frame. And then there is also something called as an acknowledgement frame. For every data frame we send, we need to send an acknowledgement, and the acknowledgement frame is also very, very small. It doesn't have any real payload, and it's a very small frame to just acknowledge the data frame. So this is really the of all the things that we talked about today, all the different types of frames, they're all overhead, and the only thing that is really useful is what's inside here in this one part that I'm highlighting right now, the frame body of the data frame. Everything else, including the acknowledgements, the beacons, the probe requests, the association requests, the de-auths, and all these things are extra overhead that we have in the channel. That is the reason why when on the box you say I'm going to get so much data rates or speeds, the actual speed you get is much lower, because you have to deal with all this overhead. So if you go back to the capture file here, you can actually see the frames in this capture file that I talked about. I'm just running a quick filter, and you can see the different types of frames. So again, you see the probe requests, probe responses, authentication, association request, association response, and so on. So if you look at the authentication, you will see the authentication algorithm, open system authentication. So the flag is set to 0. The authentication sequence number 1, which is the first frame in the authentication sequence, and the status code is successful. And then the second frame in the authentication, again, it's open system, but this is the response. So the sequence number is set to 2, and the status is again successful. If you look at the association response, you will see information about the association. You will say if this particular association is successful, and also there is an association ID. So this client gets an association ID. I talked about this in the slides. I'm showing that here in the packet captures as well. You see the association ID 1 is being given to the station. Similarly, if you look at the de-auth, again, it's the same frame header for all these frames, but if you look at the body, the de-auth will only have the reason code. So the station is sending a de-auth frame to the access point and saying, I am de-authenticating or disconnecting from you, and I'm leaving your BSS, basically your basic service set, because I'm moving somewhere else, and so I want to disconnect, right? And it uses that reason code. And sometimes the AP can also de-auth, and it can use a different reason code. There could be many different reason codes for de-authentication. So these are some of the different types of frame formats and headers. So what we talked about is all the different types of management frames. What are the fields, subfields, types, subtypes, to DS, from DS, what do they mean, and the various headers and the payloads, and which frame contains what information in the header, what information in the payload. All those details we talked about in this particular session. So I hope you found this useful, and hope I didn't confuse you too much. I didn't complete the references section, but before we post this, we'll have more references here. And that's all we have for this particular session. In the next session, we are going to jump into medium access techniques and random backoff and contention, how contention works, how random backoff works, how different types of EDCI parameters and distributed coordination function, point coordination function, interframe spaces, a number of really fascinating concepts that are there in Wi-Fi that will really help medium access work magically. And how those concepts work, we're going to talk about that in the next session.